Where'd my talk? I don't see it. I'm not going to see it. That's cool. I got it. So usually I get to do these talks. They're a little different audience, often to computer science students or more businessy situations, which I'm really happy to be among math people now. So there's actually some equations in my talk and stuff, but nothing big. So I'm going to tell you about how we use math to solve some problems at MasterCard. There we go. Okay. So here's what we're going to talk about. First thing I'm going to tell you what the company does, because I'm really tired of going to parties and stuff and having people ask me if I can give them more credit on their card and forgive them their late payment. We don't do that. I'm going to tell you what I think data science is. This is sort of a loaded term lately. I think it's trendy to talk about, at least in businessy circles. I'm going to give you 3 examples of stuff we do at work. You know, stuff my team and I have developed to make things work better. So look at that. That's brutal. So here's what happens when you swipe a credit card. We're only going to worry about the top row right now. You go to a store. That store has a bank. We call that bank the acquirer, because they get the transaction. So the swipe goes to that bank system. If it's a MasterCard, it goes to MasterCard, this building in St. Louis where all the transactions in the world go. It's pretty cool, actually. It's a great big cold room with about a gazillion servers in it. And a guy with his thumb on a button. If it catches on fire, it'll like suck all the air out. He's screwed, I guess. But then we send it. We look at the card number. Oh, this is Citibank. So we send it to Citibank. Citibank looks at the information on the transaction, says, oh, Wally's good for this, approves it. We send it back, so on. That happens in, I don't know. We get like milliseconds to do it, our part of it at MasterCard. There's other things we do. You pay at the pump. You do that right. You don't know how much you're going to get gas beforehand, do you? So that amount you get authorized for is less than what you actually pay. It's usually $1. So later in the day, we'll clear the transactions. This happens at hotels and restaurants too, because they don't know your tip, and you know, if you hit the mini bar and stuff like that. And then several times a day, we settle up between the banks. So bank A, you owe bank B this much money, so on and so forth. But that stuff's not as interesting. It's even less interesting than I think what happens when you swipe the card at authorization. So some things that I want to let you know. We don't know who you are. We don't know what you bought. All MasterCard sees is your number. And actually, most of the people that work there can't even look at that. I can because I'm fancy. But so what? It's just a number that starts with 5. We don't know what you bought. There's just a total amount on the receipt, on the message. We don't do anything with the data that you should be worried about. This is, yes, I have to say this because I get paid to say it, but it's really true. You know, there's NSA jokes and things like this. Now, if you want to worry, you can worry about your issuer, who you got the card from. So not MasterCard, but there's a bank on there. They know everything about you. Of course, they're loaning you money, and that's how the world works. So it's a lot less scary than you think. And the things I'm going to talk about are so non-scary, they might even be a little boring. I hope not. So I'll put some math in there. If you ever want to ask anything, just feel free. I really don't mind. What else? What do we do? Okay, so that's processing. That's the bulk of the business. We have this network that we own that sends transactions all around the world really quickly. and almost never fails. But we do see all this data, and it is valuable. So one of the things the company does is fraud detection. So most banks do this on their own because they're large banks and they can afford teams of computer scientists, statisticians, mathematicians to do fraud detection to determine if your score is fraudulent. But not all banks are that big. And so we will do it ourselves. We put a score on every transaction on how likely we think it is to be a genuine transaction. Some banks pay for that. We do consulting services. I don't do this. This is on the businessy side. But one thing this is kind of interesting, I think, it's called MasterCard Spending Pulse. Every month, the government puts out numbers about the economy. Spending last month in this sector was up 0.5%, so on and so forth. We do this too, and we see that data before the government. And so that little bit of time, that the day or two we can get it before the government comes out with their number, is valuable. And hedge funds buy it, banks buy it, news organizations buy it. So that's another thing. There's some other stuff, rewards. I'm not going to talk about that. There's a big philanthropic arm of MasterCard that nobody knows about because MasterCard doesn't make a big deal out of it. There's the MasterCard Foundation. There's the work that we do for the unbanked in the world. This is, I will admit, a bit self-serving, right? Because the more people that use plastic, the more money MasterCard makes. But it's self-serving in a good way because the less cash there is, the less likely people are to get ripped off or for corruption and fraud in some parts of the world that are a real problem to take place. This is part of my job. I get to do this sometimes. Is one of my favorite parts of my job is whenever that part of the company has a need for somebody to talk about data or do something with data, I'm the guy they go to. Apple Pay, does anybody use Apple Pay? Yeah, it's convenient, right? You just hold your phone out. It's encrypted. That's the real value of that. So nobody ever sees the card number on that, just the issuing bank. So you maybe have heard of when a retailer gets hacked and there's a data breach. If there's not much they can do if it's these encrypted Apple Pay type transactions, so it's safer that way. Not your problem in either case, right? Because you're not liable for any of that. Other stuff, online bill payment services. This is boring, but I'm going to say it I want to talk about it for a second because that's one of my examples. So you move. You need to get cable and internet, right? So you sign up, you often with your bank, with your checking account, and you log into that bank's website and you say Charter Communications 123 Main Street. And the money comes out every month, right? People screw that up all the time, right? They do. They put in the information wrong or whatever. And when that happens, somebody actually has to mail a check. So I'm going to let you think about that a minute. This is one of my examples. MasterCard does this on behalf of banks. So they'll take that website information from the bank and process the payment to the cable company or AT&T or whomever. So this is what I do, what my team does. Data science for MasterCard, for the technology side of the company. So not the businessy part, but the techie part, the computer part. So here's what I'm going to say that data science is. It's machine learning. This sounds fancy and scary. You already know some, right? If you know linear regression, that is a machine learning technique, in my opinion. So different ways to teach the computer to learn and find patterns and then use them to predict things. Unsupervised learning. This is a different thing entirely. If you look up in the sky at night, right, you see stars. Are they evenly spread out? They're not, right? They clump up. So unsupervised learning is a group of techniques that if you put in a picture or the data of what the sky looked like, it would find the galaxies for you because things naturally lump together. So this is looking for patterns for you rather than being taught the pattern and applying them. Recommendation systems is Google. Here's my query, places to go fly fishing in Minnesota. It's going to rank the pages. How it does that is an example of a recommender, a very, very potent, powerful, profitable one. And then there's statistics. I'm not a statistician. I don't do much in this. Things like hypothesis testing, controlled experiments, A/B testing, time series forecasting. That's a pretty obvious application in the business world. We do that. And then whatever else I want it to be, right? Since I'm talking data science right now, is whatever else I want it to be. And if somebody else were talking, then they'd get to say that. It's not a well-defined thing like abstract algebra or differential equations. It's new and unmanicured. Yes, sir?
Do you guys use neural networks for your CAM?
So, yes. So when I think about neural nets, there's pretty rudimentary ones with maybe a couple layers. And then there's what they call deep learning. I don't know if you're familiar with deep learning, but this is essentially a deeper neural network. Those, in what I've seen, how I've seen them made useful is in harder tasks like identifying objects in a photograph, like auto-captioning a photograph, for instance. So a person sitting under a tree. We don't work with that kind of unstructured data. I don't, at least, as much. So not there at that point. And another thing to keep in mind, I'm glad you asked that, the solutions that we come up with have to be fast. They have to be scalable. I think we get less time than it takes to blink to put that fraud score on the authorization. So there's not a lot of computing time available for a lot of this, for the real-time needs of things like that. But yeah, that's one of the techniques we definitely use when we make predictive models. Supervised learning. So that's the first thing I want to talk about. This is, I want to set the stage. You have something you want to predict. I'm going to go back to the fraud example. I'm not going to talk about it in detail because, frankly, I can't. I like my job. But it is one that is easy to get your head around what we're trying to do. And supervised learning is a group of techniques where you have a pile of data for which you know the answer. Here's a bunch of transactions that we know were fraudulent, and here's a bunch that we know were genuine. And then on those transactions, there's a whole host of data, of fields that we can look at to try and look for patterns. What time of day, where the card was issued, where the card was used, were you physically present, things that I think are, how much was the purchase for, right? Was it for $1 million? Because I don't think that's going to fly. This is the situation. So you have labeled data, ground truth data, we call it. the supervised learning techniques use that data to learn the patterns. It learns the patterns. You prepare the data. You think what in this would be useful. Okay, so it just says on this transaction, it just says on the transaction it has a timestamp, okay? And it has a geolocation. So one of the jobs of a data scientist is how do I make that useful so that the pattern becomes evident? And well, maybe you want to find things using your regular brain, or what we call domain expertise, to say, well, if I had a transaction this hour and the card was present in Minneapolis, and I have another transaction in an hour and the card was present in St. Louis, that's not really possible, is it? There's something wrong there. So, you know, our job is to take that raw data, finesse it into other forms so that the pattern's more evident to the algorithms. Like I said, the one you know is linear regression. I think everybody sooner or later learns what linear regression is. And if you think about it, you have labeled data. It's your observations. You use that to find a pattern. In this case, the pattern is a line or a plane. Just think of it as a line. And then you can make predictions based on that. You've turned that pattern into a formula in this case, and you make predictions based on it. So how do we use it? Let me give you an example. We have, just like AT&T or any other, Amazon, we have a big tech support team. And I don't want you to think like Wally needs a new mouse when my mouse broke once and I had to call the tech support team. I actually looked that up in a database. That's what it said. Wally needs a new mouse. Made me proud. But think about, we're selling fraud detection services to Bank X, and suddenly something goes wacky with their scores and cards are getting declined and they're unhappy. They're going to send off an email to MasterCard to say, something's broken. But it could be fraud, it could be that bill payment thing I was talking about, it could be any of these other services that we have that we offer to make money, value-added things. So some people's job is to read these emails and then, with a mouse, drag them to the right queue so that they get to the right kind of support, the fraud expert or the bill pay expert or whatever. Now, these are the same people that give tech support, and this job it's terrible. Nobody wants to do it. They all take turns cycling through it. And they're not really helping anyone, right? So what we did is I said to them, I meet with these people, and my job, a lot of what I do is word problems. You read the word problem, and then you got to turn it into an equation or some inequalities or something. In a nutshell, that's like most of my job. So here's the word problem. Can we automate this? Yeah, okay, I think we can. Do you have labeled data? Do you have a history, a pile of thousands and thousands of emails that came in along with, oh, this one was fraud, this one was bill pay, the answer? They do. And so now the idea is to use that data to get the information out of it in order to be able to do this, to have the computer read the email, so to speak. And for conversation's sake, that those columns, there's some linear combination of them, or plus a constant, some affine combination of them that will predict the log of the odds. Well, yeah, let's do a linear regression on that. That's the thing we know how to do. Now, if you take this and you invert it, you get 1 over 1 plus e to the minus junk. And that's the amazing thing is this technique works. It actually works. It seems like we made some huge assumptions here, doesn't it? And we did. But, and somebody asked me about neural networks. I have run into not many examples where a neural network performed significantly better than a linear regression in my experience. Now, I know there are such problems, and I'm not working on some of the hardest things in the field there, but logistic regression works pretty well, believe it or not. Some other techniques that do too. But this part here, this part rubs me the wrong way. So let's think about this backwards. If we want to predict the probability, what do we know about probabilities? I know they got to be between 0 and 1, right? And I know that whatever my junk is, my linear combination of these input variables, whatever that is, if it says that the probability of something is 0.99, or if it says it's 0.9999, who cares, right? It's probably true. So we want to take this linear combination of numbers and squeeze it into the interval 0, 1. Okay, so that's making more sense to me. What does this mean, this differential equation? So this is P is the probability. This is, let's think about what this says. If you've had calculus 1, we can make some sense of this. What if the probability is really small? What do you know about dp dy? So this number is near 0. So this number is near 1. So the product is near 0. So the slope is near 0. Well, this is exactly me saying that if the probability of an event is 0.01 or 0.0001, what's the difference? It's probably not true. That's just the math way of saying that. Same goes for if the probability, if it's almost certain, then P is near 1, 1 minus P is near 0. So you can solve this differential equation. This is what a solution to it looks like. And this is what the solution written out as a function looks like. Now just think of this as junk. So I know that if I want to predict the probability of something, and you're going to have to squeeze it into 0, 1, a pretty reasonable way to think of it, a pretty reasonable guess to take is that it's something that it's 1 over 1 plus e to the minus junk. And if, okay, what's junk? Well, everything's linear, right? Or almost. So let's just put a linear thing in there. Linear combination of the inputs in there. And so here's the way I think of logistic regression, this backward sense. When you start at the top and say, and I tell you, oh, let's just predict the log of the odds instead of the probability, that's so lame to me. It's a cop-out. Well, why? But when I start with some assumptions, like I got to squeeze these probabilities into the unit interval, and it's not going to be a very steep curve at either end, everything else falls out from that. To me, that makes me so much more happy, so much more comfortable. We still have some work to do, right? I have emails. I don't have a list of numbers. Right? I have emails and their answers. So how do I get this AIXI plus B out of some text? Okay, pretend you have this heinous job of reading these emails one after the other and dragging them to a mailbox. Are you going to read them all carefully? I'm not. You don't need to, do you? What are you going to do? What are some shortcuts you're going to take? And you'll still be good at your job. I'm not saying that. But what are some of the shortcuts you're going to take? Yeah. Yeah, you're not going to read every word. The is. So what, right? Well, that's the first thing we do to the emails when we process them. It's called stop lists, and they're everywhere in all different languages. Just go online. And it's basically a dictionary of words that are pretty useless in determining something about the text. And they're ones that you think they would be. Okay? The next thing I'm going to do, so now I've gotten rid of all of those. That's easy enough to teach a computer to do. I've gotten rid of all those. This application is not running. It didn't run yesterday. I want it to run. It ran before, now it doesn't run. You see what I'm getting at? All these different versions of the word run. Useless, right? So let's just standardize them to be one word, run. That's called stemming, because you just take the stem of the word. Again, some people have done a lot of work a long time ago to make this just be a tool that you can plug into. Like if you code Python, you know, it's just some package in Python to do this stuff. Finally, what I'm left with is a list of words, and what do I do with that? I got to turn it into numbers, right? Well, it's just a list of words, so let's just order them. Take all the words in all the emails and order them. Put them in a vector. You know, if the word's in there, put a 1 there. If it's not, put a 0 there. That'll work, right? We can remember first column is the word run. Second column is broken. You know, login, whatever. Are all the words that are left over equally important, you think? We could do this, and we could build a model on that, and it would work okay. I don't think they're all equally important. Some words are more telling than others, especially if you think about the problem, is this email have to do with fraud detection? Well, the word fraud is going to be really a lot more important than the word pay. So we do another trick. It's called TF-IDF weighting. It's term frequency, inverse document frequency. We just need the simplest way we can think of to assign a number to each term, each word, that will tell you how important it is. And I think that the number of times a word appears in an email divided by the number of emails that word appears in is a pretty reasonable way to do this. If this word appears in almost every email you got, then it's not going to do a very good job distinguishing between, yes, this has to do with fraud, and no, it doesn't. So there's a log there. That's housekeeping. Quotients get all wacky, right? If you think about it, their value can change a lot in a short amount of numbers. So the log is there just to mellow it out. That's all. It preserves the order of everything, so it shouldn't affect the answer much. That's the number we put in the spreadsheet here. Now we have exactly what we need. We have data that has labels on one side. I don't know why there's a C here, because there shouldn't be. It should be all A's and B's. I should have just left that alone, but I couldn't stand it. Somebody was going to call me out. We have exactly what we need. We have the labels, and we have all the numbers that represent the body of the email. And we can do that logistic regression on it and predict the probability for each one that it is about fraud or not. How do we know how good we did? how well we did. How do we know? We have some data that we didn't use in building the model, okay? It's like the test afterwards. Did you learn the pattern well? And we apply, because we're just going to get a formula. You know, if you think about this as a fancy algorithm, machine learning, it's real scary, except it's not. We just took the emails and turned them into vectors with labels and then did a fancy linear regression on it to predict the probability that the answer is what they want to be. So a little diversion. I used to be a math professor too. I worked at Wisconsin-Stevens Point. I worked at Boise State University. And I keep in touch with Eric. We were friends in graduate school. And he said, I gave an exam today. If you get here early, you can help me grade them. I bet you don't miss that. Something like that. Something very Professor Rodden-like. And it got me thinking, what did I do when I graded exams? Is I graded them, you know, assigned a number, went through them just like everyone else. And then I would take the scores and write them on a piece of paper in descending order. And I would look at them to decide what's an A, what's a B, what's a C. And then I was nice. I would never make it harder than 90 to get an A, 80 to get a B. But I often made it easier. Right? And I let the data, I let the list of scores kind of dictate where I would draw the line. Well, that's the process I want you to have in your head. So we have this holdout data that has labels. We're gonna do this grading on it. But there's only two grades, pass or fail, okay? Or right or wrong. And we're gonna write down the probabilities in descending order, just like I did with test scores. And then after 1% of the list, I'm gonna say, how many did I get right? How many did I get wrong? After 2%, right? If we did this model right, what you're gonna see is a lot of right answers at the top and a lot of wrong answers at the bottom. So this is how we do it. This is called a ROC curve, which is something receiver operator characteristic. I don't know. ROC curve. It's how we tell how well we did. It's a parameterized curve. So that's why I have an Etch-a-Sketch. You know, the x of t, y of t. Everyone played with an Etch-a-Sketch, right? That's how I think of parameterized curves. We are going to, we look at this, you see two curves. This is the blue one is a curve from our model, and you see this diagonal, the diagonal. So that's guessing. If you randomly assigned an answer, if you randomly assign a model score, a probability, just you made it up. You sorted the list in a random order. If you went through 10% of the list, you would have 10% of the false positives and 10% of the true positives. If you went through 20% of the list, you'd have 20% of the true positives and 20% of the false positives. And you'd only have all the data when you got through the whole list. But it wouldn't be any better because the distribution of right and wrong answers wouldn't be bubbling up to it would be uniform along this list. You wouldn't see all the right answers at the top. So this is guessing. This is our model. We do the same thing. So if I look at this, I see that, well, I don't have the parameter on here, but let's say this is 10% of the data when I get to x equals 0.2. I know that if I cut off the list there, I'd have 90% of the all the ones that were fraud and 20% called fraud that weren't. So this area, this number here, well, we don't usually subtract a half from it, though we should. This area is how much better than guessing you were. Remember, this model does not spit out an answer. This one's fraud, this one isn't. It doesn't do that. It spits out a probability. So you have to decide at what point do I cut it off and say everything above this is yes and everything below it is no. That's kind of weird to get your head around at first, but that's the basic idea. And that's all of the supervised learning I'm going to talk about. I want to get to a little bit less mathy and a little bit different stuff, if that's all right. Another thing we do, information retrieval. And I touched on this with the bill paying thing, when people enter their information wrong. So I kind of blew it with this, but I got a little ahead of myself. But here is an example of how I might screw up my cable bill, or somebody might screw up my cable bill. I pretend I'm the cable company. I don't care. It's just data. Well, I need to know that this person that entered this really meant that top row. Right? Otherwise, MasterCard has to actually cut a physical check instead of processing it electronically, and that costs like a gazillion times more. Right? It used to be that if it didn't match perfectly, one of the things in the list, one of the payees, one of the businesses in the list, then that's it. Too bad. We're going to cash, and we're going to do it every month, you know? And so I thought, that's dumb. Maybe we can do some math to help this. That's the problem. Here's a technique. It's a lot like the text, the natural language processing. I believe it's latent semantic analysis is the name of a technique. This is adapted to this. So we had emails with words. Now we have strings with characters. I'm just going to say letters, but there's also space and the digits, right? We're going to break each word up into pieces, into what are called n-grams, 2 grams. So my name, Wally, turns into those 4 rows of data. W-A-A-L-L-L and L-Y. And it's just going to be in a vector. How long is the vector? Well, it's this long. Letters, digits, space. I start everything with a space and end everything with a space, so I don't lose any information about starts with, ends with. And these weights are this exact same scheme as before. So not all 2 grams are as indicative of how, are not all equally important in a word, in a name. Starts with W is less common than something that has an AL in it, so it gets a higher weight. Okay? So now I've taken these strings and I've turned them into vectors in space. There's DNA here because, and I'm not positive, but I kind of looked at a paper once where they did DNA matching using this technique. If DNA being a word, a really long word in a 4-letter alphabet, right? And they didn't do 2 grams. They did much longer chunks to compare, but so this is kind of borrowed from that world, I think. I tell bosses at work this because then they get all swimmy-eyed. Oh, this is like DNA matching. This is cool. It's fun. So this is what really amazes me. I've turned the strings into vectors, high-dimensional space, but just think of 3-dimensional space. Wouldn't it be amazing if nearby strings, so like misspellings, were nearby vectors? Is there a way to define similarity, so like distance, in such a way that makes that true? Well, what does string similar mean? What is similar? What is, Wally, and then I always thought this was a simple name, Wally, but apparently it's really uncommon. And so like if I go to a restaurant, like fast food, and what's your name? I get W-A-L-L-E, W-A-L-I-E-E-Y, you know, there's these crazy. Somebody wrote Lawley once, L-A-W-L-Y. I like to still call myself Lawley every once in a while. My wife hates it. What does it mean, string similar in that case? Well, it means, think about Wally with a Y and with an EY. The first one is 4, 2 grams. The second one is 5. I think they share 3, off the top of my head. So string similar means shared 2 grams. Well, look at the dot product. These are vectors. I like to take dot products of vectors. I'm a mathematician. Remember, each AI and BI is if it's a place in that vector. So how does it happen that AI, BI is non-zero when you take the dot product? Only one way this can happen is if both words, both strings have that 2 gram. Otherwise, one doesn't, so either the AI or the BI is going to be 0. Right? So the more 2 grams, more string similar. String similar means shared 2 grams. Shared 2 grams mean a larger dot product, a larger inner product, that some will be bigger. Well, I'm going to make everything length 1 because I like to. What does that become? It becomes the angle, the cosine of the angle. And this is how we do string similarity and matching in these problems. And the solution that we did was to build a system that takes all the registrations from one night and matches them up against all the possible companies that MasterCard processes bills for, and says, this one, all the ones that don't match already, and says, this one, which one's it like? This one, which one's it most like? So on and so forth. And it does this wicked big Cartesian product. We do this in even a bigger scale on something else. And then here, in this case, that all gets fed to some people that work in this department, some entry-level people who say yes, yes, no, and then they correct it, and then everybody's happy, right? I just think that's amazing that nearby strings have nearby vectors. It's really clever. I'm almost done. One last thing I want to talk about. Oh, yeah, fire away.
Supervised learning technique as well as
Mm-hmm.
I'm not sure if you guys have an idea of UST rate or if you want to error rate.
Yeah, so yes, absolutely. And it all starts and ends there, because if it doesn't work, nobody's going to pay me to do it, right? So for instance, the emails, we've repeated that process many times now. Typically we cut the score off and we get 90% right. This is a harder problem from a computing standpoint, because the amount of computer you need to do, it's called a nearest neighbor problem, it's a Cartesian join. It's daunting, to say the least. This I'm not sure how I'd say accuracy, because it's just saying this is similar to that. If it's a 1, they're alike. If it's a 0, they got nothing in common, right? There's not a yes or no. I know that we do this on, I'm not going to get into the details because it's kind of boring. MasterCard, Visa, we don't need to know who the merchant is. All we need to know is who Bank A and Bank B is, and then, do this, let them talk to each other. We want to know who the merchant is for a lot of reasons. Help with fraud detection, for one thing. So big part of my responsibility is helping to maintain a list of all the MasterCard accepting addresses, businesses in the world. And they're like, well, I don't know, Square kind of screws that up, and Google Pay a little bit, but probably like 40, 50 million. So we do this on all the new merchants we see every night against that giant database. And I know that in the US, it's found like 1 million merchants that we were getting wrong, that now we're getting right. So, and that one is more complex. Nobody checks the answer. I just have to make my best guess.
And I was also curious, back to the supervised learning. Curious what kind of tool you use to build and train these models.
That's a good question. So I'm old, and I use SAS. It's a statistical language, SAS and SAS Enterprise Minor. It's a GUI interface. The younger people that know more about this than I do that I hire, computer scientists and so forth, they use either R, which I imagine you all use here, and Python, which I also imagine you all use here, right? Those are the tools we use. We use MATLAB for something I'm about to show you, for some other stuff as well. And the way we store data is like a whole nother talk, those tools. So, is that good? Yeah, good. Where should we go out to eat? Everyone's had this conversation, and it gets really old, doesn't it? You always go to the same places. So here's some foray into the world of recommenders. This was just some researchy stuff I did. We don't build a product on it or anything. But you know how I said we have a list of all the merchant locations? Think of just the Twin Cities and restaurants. Okay, so there are probably 3,000, 4,000 of them. I'm going to build a graph where those restaurants are the vertices, the nodes. Say vertices, right? We're mathematicians. Computer scientists say nodes, so I'm going to lose either way. We're going to build a graph where the vertices are restaurants. And I'm going to put an edge between two restaurants, two vertices, if the same card has visited both. Now, there's going to be a lot, right? So really, I do something, I weight the edges. If there's no edge, then the same card has never been to both, which actually is usually the case. But we'll weight the edges by the degree to which they are co-visited. Now, this idea came to us because I'm kind of a foodie, and I'll go out to eat, and if I really like the place, I want to get up and I want to say, you like this too. Where else do you go? Right? I want to be obnoxious and ask everyone, because if we both like it, chances are I like the other place. That's where this came from. This is a picture of 3 of the suburbs of St. Louis, where our office is and where I live. And, you know, a graph has no canonical, no right way to display it. Right? So we have some tools. This was Gephi is what it's called. It's an open source graph analytics tool that I use to cluster, to display the graph. And the way it works is the heavier the weight, the more the two vertices, the stronger the edge between two vertices, picture a spring, the more it wants to pull them together. Okay? While at the same time, all the vertices have, say they're all negatively charged, so they all want to repel each other. So this is an algorithm that will come to some minima, some steady state solution, and form groups. This is where I live. There's across the river where my office is, these are 2 other suburbs, and you can see something not terribly surprising, that when people go out to eat in Chesterfield, Missouri, they often go out to eat in Chesterfield, Missouri. Right? They don't go to O'Fallon, Missouri as often because it's further away. But then we did this for most of the country. And the thing about graphs is you can put them, you can represent them as a matrix, and you lose 0 information. They're equivalent. The matrix has the rows, columns are the vertices. And the number in that entry is the weight of the edge connecting those vertices. So here is several thousand restaurants in the St. Louis metropolitan area. And the picture of that matrix was made by just coloring that pixel or that area, that entry blue, if it weren't 0. And so what you get to see, I think, is this really cool picture of the St. Louis restaurant market. This is, I know nobody's probably from there, so you'll have to take my word for it a little bit. This is St. Louis County, which is the city, it's where I live, it's where most of the people live. St. Louis has the Mississippi River and the Missouri River. A lot of the so I'm on in that wedge of land with St. Louis. A lot of St. Louis is St. Charles County, which is on the other side of the Missouri River. It's a big river. People there are famous for never leaving. It's like Stepford. It's the suburban hell. It is. And you can see this behavior. Look at how dense the St. Charles County is in there. I think that's awesome. I mean, you can see this human behavior just in the physical form of a matrix. So this is how we use it to make recommendations. And you know, it's a variant of PageRank algorithm. It's almost 6:30. I'm really mostly excited about this picture. I don't feel like going through a Markov process and blah, blah, blah. So I'm going to stop. We got a couple minutes. Y'all can ask me questions or anything you like. Is cool. So.
Let's thank our speaker.
Thank you. Yes, ma'am.
Oh, go ahead. I was just wondering if you have looked at latent semantic analysis in higher dimension.
So for like making the n and the n-gram bigger, yes, I did start to look at that, and the information gain was not worth the computing trade-off. Does that make sense? Yeah.
Well,
And the strings
I'm
are
going to dinner, so we can.
the strings are pretty short.
I use this in my research.
Oh, okay, cool.
I'm just curious about one of the lines where you asked for G analytical techniques to the error.
To compute what?
The error.
Oh, yeah. Absolutely, yeah. I mean, it seemed to...
You can actually get there.
Oh, yeah, absolutely, yeah. Mm-hmm.
Let's thank our speaker again, and all of you around the applause.
Thank you.